So I'm Sauvik. I'm from Georgia Tech, but this is work that I did with collaborators at CMU. Now, I hate to be the bearer of bad news. This talk has nothing to do with virtual reality, but right after this talk is over, I promise you'll go back to your regularly scheduled programming. I appreciate the creativity that the program chairs had to put into putting my talk somewhere. So anyway, it's April 26th. The UIST deadline has just passed. You've been putting in long days. All you want to do is Netflix and chill. And yet, you are presented with the dreaded login screen, right? It's like it's been months since you last logged in. What was your password again? Pretty sure it started with password 12345, but that was the first one. You've reset it several times since then. Oh, it must be like QWERTY or something. So you try, and eventually you just give up, fall asleep, and call it a day. Anyone else relate to this problem? So this scenario is one instantiation of a broader class of problems that I like to call infrequent authentication. So this is when you need to log into accounts with super long persisting sessions like Netflix, Facebook, Twitter, what have you, or increasingly for sort of the IoT devices that this community and other communities are developing where maybe you share sort of a physical device that you only access once in a while, right? Like maybe a conference room or something that you need to authenticate yourself into, but you do it maybe like once a week, twice a week. For these situations, you really need secrets that are memorable so that you remember it after a month, after a week, whatever, that are secure because otherwise there's no baseline value in having the authentication at all, and that are deployable. And this is an important one that's typically forgotten in authentication work. It needs to be something that is easy enough for users to implement given the importance of the task, right? So, for example, I could just use a biometric reader and put it on every single device and give that information to every single account. But I personally don't want to deliver my biometric data and have it be secured by a bunch of different third parties, right? So in these situations, what we really need is some sort of combination of this usability, security, and deployability. I'm not going to go into each of these cells over here, but broadly speaking, the existing solutions to these sort of authentication techniques are alphanumeric passwords, which we're all familiar with, graphical passwords like Android's 9-pattern lock and the Microsoft sort of touchpoint password, and of course biometrics that we all know about. And it turns out for infrequent authentication use cases, graphical passwords provide a lot of great properties in that they're very memorable typically, and that they require non-invasive or no specialized hardware. However, there's a problem, which is that graphical passwords typically have very weak security, right? So there's limited search space. If you take Android 9. As an example, there's a limited number of moves you can make. And also, it's easy to break usually via common attacks like the dreaded shoulder surfing that everybody likes to talk about, where somebody's just sort of looking over your shoulder and trying to figure out what your password is. Usually you can figure it out with one attempt. And also, existing graphical passwords are not built for this use case where you're only entering your password in like once a week. They're typically built for the use case where you're entering them like once, twice, 4 times, 10 times a day, right? Like for your phone or for your computer or something of that nature. So what's really needed is this form of graphical authentication that is quick to imprint so that you don't need to enter it like 10 times before you really memorize it, that is long-lasting so that you can go away for a week, work on your WISP paper, and then come back and still remember it, and that is resilient to common attacks like shoulder surfing, random guessing, brute forcing, things of that nature. So when we started thinking about the design space for like how can we approach this problem in a way that's interesting, we were really inspired by the ancient Greco-Roman mnemonic technique called the method of loci. Many of you are probably familiar with this. It traces its roots back millennia. Actually, ancient Greco-Roman orators used it to memorize speeches that they used before there were lots of great external memory aids. And it's still used by quote-unquote memory athletes today to memorize, for example, arbitrarily long digits of pi. And the basic premise of this approach is that all of us in our head have essentially really strongly imprinted cognitive maps of places that we know, right? For example, your childhood home. You can probably close your eyes right now and imagine how to get exactly from your front door to your living room, to your kitchen, to your bedroom without batting an eye, right? If you could bat your eye while your eyes are closed. The key insight over here is that the human visual-spatial memory system is clearly very strong because it's been used for millennia and memory athletes use it to this day. and yet it has not been thoroughly explored for the context of authentication. And so we thought maybe we should change that. Maybe there's something to using this approach for authentication. So that led us to this research question, which is, are Visual-Spatial secrets, as opposed to just purely graphical secrets, in a virtual memory palace, more memorable and secure than standard graphical passwords like Android pattern lock? And for that, in exploring that research question, we introduced this new form of authentication called the memory palace, in which secrets are encoded as paths in a 3D virtual labyrinth that users can navigate using standard touch gestures. So how did we get there? So broadly speaking, we had these 3 steps. We use an iterative design process in order to get to the point where we could actually evaluate and test this research question, right? For time purposes, I'm not really going to go into this first step of our iterative design process, which is perspective exploration. But essentially, we implemented a bunch of low-fidelity prototypes of encoding these visual-spatial secrets as a two-dimensional path, or a 3-dimensional path navigated in third person, or a 3-dimensional path navigated in first person. And the upshot of all of that was palaces should be 3-dimensional, and they should be navigated in the first-person perspective in order to enhance memorability. That makes sense, right? That's how we navigate the real world, and that's how our visual-spatial memory has been evolved to be taken advantage of. So that's what we did. So how did we design this system ultimately? So at a high-level view, what we used was procedural content generation techniques, which has been talked about a little bit in the past in this conference as well. Essentially, we implemented a proof-of-concept version of the memory palace on Android using OpenGL, but I want to emphasize we don't really see the memory palace as being useful as like an everyday authentication technique. This was just a proof of concept to show that it could work. Essentially, we created a 3-dimensional palace that can be navigated in the first-person perspective. We employed procedural content generation techniques to randomly construct visually distinctive rooms. And then we had users navigate the palace using standard touch gestures. So we started with this 21 by 21 grid, but that's arbitrary. In theory, the palace could be infinite, right? As users get close to the edge, we can use procedural content generation techniques to make the palace larger and larger and larger. And that gives us a nice property in that our search space is not limited, right? It's a theoretically infinite search space, which has some good security properties. We used a genetic algorithm in order to stochastically split this grid into Tetris room shapes, so the classic I, L, T, and block. And then we placed doors between rooms along adjacent walls. So if you start with this blank, simplified grid space, essentially what we did was we started using this genetic algorithm to fill out the grid space into these different Tetris shapes. And then we placed doors randomly along adjacent walls such that any 2 rooms that are neighbors, there is a way for the user to navigate to those different rooms. But that wasn't enough, right? So room shapes being distinctive is good, but you're still in this labyrinth, and labyrinths are tough to navigate through. So we want each room to be visually distinctive, right? So we added terms to the fitness functions to not only generate the room divisions to be somewhat distinctive, but also so that each room looked visually distinctive. And the way we did that was, it's essentially a coloring problem, right? So we had a bunch of different floor and wall textures, and we ensured that adjacent rooms have different floor and wall textures. And we also wanted to make each door within each room distinctive in some way. And so each door was textured differently, and we also placed different artwork and decorations around those doors such that each door could not be confused for one another, in theory at least. And of course, as you saw in the video, users navigated the palace using touch gestures. So in the memory palace, authentication secrets are specific paths through the space. It's not just the start and the end point. It's everything in between. So if you double backed, that's part of your secret. And that also makes the search space of the authentication secret larger, right? So of course, to register a secret, you do the password confirmation approach, right? So you start recording yourself navigating through the palace, and then you put it in again, and then that's a registered secret. Of course, we gave users the ability to freely explore the procedurally generated palace first, so that they could get familiar with the space. And then to authenticate, user simply needs to recreate the pre-registered path exactly the way they put it in, right? Okay, so that's the system. So now let's talk a little bit about if it actually works relatively better than a standard graphical password. So in general, we had these 3 hypotheses going into the evaluation, right? So controlling for secret complexity, and this is important because we wanted apples-to-apples comparison. And relative to Android 9.pattern lock, which we use because it's a very popularly used graphical password out there, and we just wanted to compare it to something that people are familiar with, we had the following 3 hypotheses. 1, that Visual-Spatial secrets in the memory palace should be more memorable after a period of extended disuse than Android 9.secrets. 2, that Visual-Spatial secrets in the memory palace should be more resilient to common attacks like shoulder surfing. I'm not going to argue for the other common attacks like brute forcing because that just follows from the theoretically infinite search space. And 3, that Visual-Spatial secrets in the memory palace should be probably slower to enter because you're not just drawing a shape on a screen, right? But we wanted to quantify what that difference might be. So broadly speaking, we ran a counterbalance within subjects experiment with 2 weeks separated by with 2 sessions separated by 1 week. In the first session, we essentially showed participants a 9-dot and a complexity-controlled memory palace secret in counterbalanced order. We had to give them a secret instead of having them generate one, so that we could ensure that the complexity of the secrets was the same. Because if one was super simple and the other was very difficult, then that's not exactly an apples-to-apples comparison. And then we showed participants the secret twice, and then we asked them to replicate the secret themselves to show that they had learned it. And if they didn't, we would show it to them again. But in practice, no participant needed more than 2 attempts in order to show that they had learned it in that particular session. The second session was at least 7 days later. Some participants came in 8 days later, but on median 7 days. And essentially the first thing we asked them to do is recreate the memory palace and/or 9-dot secret in counterbalanced order again. We gave them 3 attempts to do so. We gave them no visual aids, no memory aids at all, just recreate what you learned in the past. And if they didn't do it in 3 attempts, we considered it a failed attempt to remember their secret. Otherwise, they would have remembered their secret. And then after that, in order to test the resilience of this technique against a common attack, shoulder surfing, we essentially recorded one of us entering the secret for 9-dot or memory palace from an over-the-shoulder perspective and showed it to participants twice. And then we asked them to recreate the secret they had just seen in the video a few seconds earlier. So our measures are basically one-to-one correspondence with the hypotheses we had. So for memorability, we measured the accuracy of the users re-entering their secret in session 2. For shoulder surfing, we measured the accuracy of breaking the over-the-shoulder secret shown in session 2 through that video. And then finally for speed, of course, we just trivially measured the speed of entry. So we recruited 20 participants from the greater Pittsburgh area, 10 male, 10 female, age range of 18 to 44. And here are our results. So our results are pretty good. So memorability after 1 week, 70% of users remembered their memory palace secret after 1 week, compared to just 30% of users who remembered their Android 9-dot complexity controlled secret, which is great. It's a 2x improvement, more than 2x improvement. The shoulder surfing results are even better. Only 5% of users were able to recreate the over-the-shoulder perspective video for the memory palace versus 65% who were able to recreate the over-the-shoulder perspective of Android 9-dot secret, again, complexity controlled. And then finally, entry speed, while the result was not statistically significant, we imagine it's just because we didn't have enough participants for this particular result, but the memory palace was a little bit slower, about 4 seconds, which would be terrible if you had to do this 10 times a day. But if you have to do it once a week, it might be tenable given the significant improvements to memorability and security over there. Now, before I conclude, I just want to state that one of our co-authors, Taehoon Lee, was an undergraduate who worked on this project. He did a lot of work regarding the development of this project. He wanted to do a PhD, but unfortunately he passed away in 2017 and never was able to get there. I have no doubt that he would have been great at doing research, and this paper, I hope, serves as a good tribute to his memory. So with that said, that was the Memory Palace. I'm Sauvik, happy to take questions.
Wonderful. I see a question in the back there.
Thank you. Hi, I'm Katharina Weinecke from the University of Washington. This is great work. I love the paper. I'm someone who's notoriously bad at navigating environments and new houses, new buildings, and so on. Mm-hmm. So one thing that I was wondering about is if you were able to personalize the environment and, like, let's say, give me via Google Street View my own neighborhood or something. Mm-hmm. Do you think this would increase quite a bit, or what's your? Have you been thinking about this?
Yeah, that's a great question. So that's, people certainly have different perceptions of their ability to wayfind in, 3D space. That's definitely true. It's probably, like, almost every human, though, is better at that than remembering arbitrarily long strings of alphanumeric characters, though, which is why we decided to pursue this approach. I think the second part of your question, though, which is, can we personalize this, I think is really interesting. We didn't actually explore it. There's a trade-off. If I give you the street view of your neighborhood, there's more information an attacker can exploit, right? Because there might be sort of more contextual information of the Seattle area or something like that they can potentially look, and then they can use entropy-based techniques to figure out, okay, you're more likely going to go left here than right or something like that. But I do think that relative to the usability gains, that's an open question, right? Like, is the usability gain so much better than the security loss? I'm not sure, but I think that would be super interesting to explore. Yeah.
How did you give the participants what is the actual path to walk through? Was it as a viewing of a walk or as a top-down map?
Yeah, so it's actually a viewing of the walk itself. So when showing participants the path to follow, we had them look at one of the researchers entered the path for them, and they were asked to replicate that path. That is exactly over the shoulder, yeah, but in this perspective, it was interactive, right? It was like, first you go up, then you go right, then you go up. It wasn't just watch me do this thing.
Yeah, hi, I'm Jackie. I'm from Stanford University. Great work. I really like it. One thing I'm thinking about is like for regular like alphabet-based passwords, we have like we already built a lot of training stuff, and so that people can create a secure password for that. So do you have any insight on how to make user create a secure password in like your kind of password for your kind of password?
Yeah, that's a great question. I think with alphanumeric passwords, we benefit from decades of experience of it. So in short, I don't actually know what would be the best way